Hey, what's up, Chem peeps? Let's talk about how we can prepare our own buffers. Now, anytime I'm doing a buffer problem, I will always write out this equation. Boom. I suggest that you do the same. All right, let's take a look at this problem. It says which acid would you choose to combine with its sodium salt to make a solution buffered at pH 4.30? For the best choice, calculate the ratio of acid to base required to attain the desired pH. And as you take a look at your screen and in your notes, we're given a table of 4 different acids and their Ka values. Boom. All right, the first thing I'm going to do is I'm going to think about what is the hydrogen ion concentration when the buffer solution has a pH of 4.30. Recall that pH is equal to negative log of hydronium ion concentration. If our pH is 4.30, how do I solve for x? Divide each side by -1, then let's go exponential. Second, log negative 4.30 x equals 5.0 times 10 to the minus 5 molar. That is my hydronium ion concentration. Boom. Now, why did I do that? We're trying to prepare a buffer with a specific pH, a specific hydronium ion concentration. And remember, anytime you're working with buffers, you want to think about this, because it's the weak acid and the conjugate base that are contributing to the hydronium ion concentration and the pH. And remember, in a good buffer, you're going to have equal concentrations of your weak acid and conjugate base. And when they are, this part of the equation essentially drops out. So if we're looking to prepare a buffer with a pH of 4.30, we're looking to prepare a buffer with a hydronium ion concentration of 5.0 times 10 to the minus 5. And if we're trying to choose a weak acid to prepare this buffer with, the hydronium ion concentration needs to equal the value of our Ka, or be as close to it as possible. So as I scan my list, I look at the Ka values and recognize that benzoic acid is our winner. It's the one that has a Ka value that's closest to the hydronium ion concentration that we want, aka closest to the pH that we want. Okay, so we have chosen our weak acid, benzoic acid, to prepare this buffer. But the pH isn't going to be exactly equal to our desired pH. It's going to be close because the Ka is close to the hydronium ion concentration that we want, but it's not exactly. It's a little bit larger than that. So if I prepared a buffer with equal parts weak acid, our benzoic acid, and its conjugate base, the benzoate ion, my hydronium ion concentration would equal 6.4 times 10 to the minus 5. And the pH of a solution that has a hydronium ion concentration of 6.4 times 10 to the minus 5, boom, quick jump to my calculator, negative log 6.4, second E, negative 5, close parentheses, answer. The pH would be a little lower than I want, about 4.2. And the desired pH is 4.30. As we think about this ratio between acid and base to adjust the hydronium ion concentration and therefore our pH, adding a greater amount of acid, making this numerator value larger, would increase the hydronium ion concentration, decrease the pH. So we need to add some conjugate base, increase this denominator value to decrease the hydronium ion concentration and increase the pH. So the question is, what is that ratio? We know it has to be less than 1. We need more conjugate base than we have weak acid. So how can we figure this out? Well, I'm going to rewrite my expression for the hydronium ion concentration for a buffer. Boom. But notice what happens here when I divide each side by Ka. I set up a ratio between my hydronium ion concentration and the Ka that we can compare to the ratio of our weak acid to conjugate base. And because we know the hydronium ion concentration that we want our solution, our buffer to have, and we know the Ka of our weak acid, we can determine the ratio of weak acid to conjugate base needed to obtain the pH that's desired. So the hydronium ion concentration that we want, 5.0 times 10 to the minus 5 over our Ka 6.4 times 10 to the minus 5. That's going to equal our ratio between our weak acid, benzoic acid, and its conjugate base, the benzoate ion. Calculator time. parentheses 5.0 second E negative 5 close parentheses divided by parentheses 6.4 second E negative 5 close parentheses answer. We get a ratio of 0.78. Boom. So what that means is I would need 0.78 moles of my weak acid, my benzoic acid, for every 1 mole of conjugate base. Again, it's a ratio of weak acid to conjugate base. Again, come back to this expression. Always come back to this expression. If it's not a 1-to-1 ratio between our weak acid and conjugate base, but a ratio of 0.78, and we multiply that by our Ka, 6.4 second E negative 5 close parentheses. Notice that we get the hydronium ion concentration that we want for our desired pH. Boom.